I'm Daphne. I'm a third-year PhD student, and I'm going to tell you a little bit about cardiovascular physiology. And so to divide up the talk, the three main goals of our learning here are to understand some foundational ideas about the cardiovascular system and cardiovascular physiology. Then I'm going to discuss a particular mechanistic model for the cardiovascular system called Windkessel model, which is very old and foundational, I would argue. And third, I will briefly touch on a particular disease state, pulmonary hypertension. And so before we really dive into this, I think we have to answer the question, why study physiology in the context of work in machine learning and computational medicine. So in the Stultz lab, we use modern machine learning methods, but we propose that well-understood deterministic models of physiology can inform statistical models and improve their results. And Collin will show that in a couple minutes with his presentation of our work. Secondly, and perhaps more importantly, this is a quote from a paper from your very own Dr. Sarma and Eric Reinertsen, a postdoc in the Stultz lab. And I'll read it. Basically, physiology, a discipline that is the basis of medical education and decision-making, provides a rich set of concepts to inform the development of ML models that can be vetted and transparently understood by clinicians. I think it's a great quote. I'm not just sucking up. And I think that, in essence, physiology is the language that clinicians speak. And if we put our machine learning models into that language, then we can achieve greater interpretability. And to discuss a little bit more about this issue of interpretability / explainability and how we think about it in the Stultz lab, traditionally, or I don't know if that's the right word, you might imagine that there's kind of a trade-off between explainability and performance, because a simpler computational model might be more explainable because the mathematics is more intuitive and basic, but that model's performance might be decreased because the model has less flexibility and power, whereas a deep model might have very high performance, but very little explainability. So I want to argue basically that this is not really the right way to look at our models. So I want to consider an example of, let's say, classifying the ECG for whatever downstream task, whether you're producing a risk score or classifying arrhythmias. So there's basically two parties here, at least two parties. We can think about the cardiologist. I'm gonna get my pointer, sorry. Think about the cardiologist and the machine learnist who makes models. And so the traditional approach to extracting information from the ECG, the normal clinical approach, is that a cardiologist reads the ECG and has basically an algorithm and a series of rules by which they extract information about the patient's heart and physiology. And so this set of rules is, I would argue, very interpretable to the cardiologist. There's an exact association between changes in the ECG and changes in physiology. For a machine learnist, the blue over here, I would say, because maybe of their limited clinical background and less holistic knowledge of physiology, but hopefully we're fixing that today, they would find that to be less explainable, and of course the performance is the same. Then when we consider deep networks, I think that they're largely not super explainable to anyone, but I think that machine learnists, we have heuristics for why models do things and why they work and when they work. And cardiologists see that type of thing and don't know why it works or what's going on. And this is not like a burn on cardiologists at all. It's, it's a very, it's not an explainable platform. And so essentially what I'm saying is that this relationship, this green curve, whatever, doesn't hold. And I want to propose, a little optimistically, that if we have clinical models that are informed by physiology, that they can be both explainable because they're in the language that clinicians speak, and they can have high performance because you can boost modern machine learning methods with this physiology. I also want to argue, kind of as an aside, that models which can't be explained should not really be regarded as powerful or high performance in the first place. So the example that I like to think about is if you imagine a risk model, let's say, that takes in a patient's medical record and predicts their risk of an adverse event. If that model is perfect for 95% of patients and completely wrong for 5% of patients, that's not actually a practically useful model because the consequences of a wrong prediction are severe. And if you don't know which patients the predictions are wrong for, then you can't reasonably use this model. It's not translatable into medical applications. And by the way, if anyone has any questions, please feel free to interrupt me. That's how we do our lab meetings, so I'm very used to it. Okay, so now I'm going to talk a little bit about hemodynamics. So this is a diagram of the type that you may have seen in a high school biology textbook or in a medical school textbook. And essentially, you can have this very detailed representation of the cardiovascular system and all its vessels that deliver oxygen and nutrients to tissue. And what I'd like to argue is that while this conveys anatomic details, it doesn't really convey any information about physiological function. So we're not going to look at pictures like this, except just now. I also would argue that from a modeling perspective, you can use finite element models and other such tools to simulate these complex hemodynamics in small vessels extensively. But from the perspective of our work and in general, it's not clear what you buy clinically with such simulations. So instead, I'm going to introduce this diagram of the cardiovascular system. And so this pinkish square is the heart, which is functionally, from an engineer's point of view, a pump. And blood is ejected from the left ventricle, flows through the body and delivers oxygen and nutrients to all your tissue, including the heart itself, and then flows back into the right atrium, is pumped into the right ventricle, and then pumped into the pulmonary circulation, which is where gas exchange occurs and the oxygen binds to the hemoglobin and red blood cells, and we get oxygenated blood, which does the whole dance over again. And so if you were an engineer that built the system, I think what you would want to know in order to evaluate its functionality and health would be pressure at different points. And so you can have pressure that's too low. So what you would see in that case would be insufficient circulation of oxygen and nutrients, oxygenated blood and nutrients to tissue. And so you will have tissue damage and death. You can also have pressure that's too high, which will cause damage to the system itself, which is literally what we see in cardiovascular medicine. And so then the follow-up question to that is, how do we actually practically measure pressure in the cardiovascular system? So there are two gold standard tools, and they're kind of the same thing. We have right heart catheterization and left heart catheterization. And so this is a procedure where a catheter with a pressure transducer is inserted through a large vessel and snaked through your large vessels into your heart and measures pressure in different chambers. And so in right heart catheterization, if we go back to this picture, in right heart catheterization, you're coming in on this side and you're getting pressure in the aorta, which is the large vessel that ejects blood, oxygenated blood from the left side of the heart into the left ventricle and measuring pressure there. And you can go into the left atrium. It's not common. You're going against the flow of blood, so it's not really practice. So you can get two important pressures there. And then in right heart catheterization, we're going to look at this handy picture. You insert, the catheter is inserted through a vessel such as the central jugular in the neck or a large vessel in the groin, and it's snaked into the right atrium where it's passed through the tricuspid valve into the right ventricle and then into the pulmonary artery and So let me back up a little bit. So it's put into the right atrium and you can measure the right atrial pressure. Then you get the right ventricular pressure. And then once the catheter enters the pulmonary artery, you can get the all-important pulmonary artery pressure. And then what's done next is, so the type of catheter that's used for right heart catheterization has a balloon on the end, and the balloon is inflated and the catheter is wedged into a vessel in the pulmonary circulation. And essentially what you get there is you get a static column of blood between the catheter and the left atrium, right? Because the blood goes from the right ventricle to the circulation to the left atrium. And so that's a proxy for pressure in the left atrium. So this quantity that we call pulmonary capillary wedge pressure or pulmonary arterial wedge pressure is equivalent to the left atrial pressure.
Daphne, just a quick question, maybe to give some of the listeners some context. So you were talking about how, from an engineering standpoint, you might think about the heart as a pump. And so like the catheterization, that's not something we would do in a healthy person, right? This is something where we would do this if something is wrong and we're trying to characterize this like very fundamental physiological parameter.
Yeah, exactly. That's a good point. So catheterization is a highly invasive procedure. It requires significant skill, and anyone who is having a cath has already undergone a series of other diagnostic tests, including the electrocardiogram, probably an echocardiogram, which is an ultrasound of the heart, various lab tests, which indicate that this person has some dysfunction in their heart, which needs to be further validated with a cath.
And in the figure, which pressure is being shown?
In these tracings?
Yeah.
So it's kind of showing a cartoon of what you would see if you were in the cath lab and you were moving the catheter. So first you would enter the right atrium and you would have a waveform like this. Pressures are pretty low. And then in the right ventricle, the force of contraction is greater and you're going to have these larger pressure waveforms. When you enter the pulmonary artery, you see the pulmonary artery pressure like this, and then the wedge pressure is this proxy for the smaller atrial pressure. Again, the force of contraction is less in the atria because there's less muscular tissue contracting. Does that answer the question?
Yeah, so it's the pressure where the catheter is.
Yes. Yeah. And so realistically, during a cath, the clinician's going to just, or the software is going to read off a number of individual pressures from these waveforms, particularly the mean pressure and the systolic pressure, which is the highest pressure, and the diastolic pressure, the lowest pressure. Those are kind of the important clinical values. And so a few more quantities that we measure during a cath. So cardiac output is the flow rate from the aorta, usually measured in liters per minute. Now take note, because blood is basically a Newtonian fluid, and because of conservation laws, the flow rate in the aorta is going to be the same as the flow rate in the pulmonary artery, etc. You also have stroke volume, which is the volume ejected by the heart per beat, and that's equivalent to the cardiac output divided by the heart rate, right? So it's how much flow happens per heartbeat. And then you also have this all-important quantity called vascular resistance. It affects basically how much of a pressure drop you're going to see over a particular vascular bed, and it's a function of the material properties of a blood vessel. So this expression is one model for resistance in tube-shaped vessels with water going through them, or fluid, sorry. So L is the length, eta is the fluid viscosity, and R is the radius. And so basically, if you have a blood vessel, a wider blood vessel will have less resistance than a more narrow one. And that's kind of intuitively sensible. And if we think about some of our physics and electrical engineering knowledge, this is strongly analogous to resistance in an electrical circuit, right? So if you have, let's say, some piece of metal that you're measuring the voltage drop over, the shape and size and material properties of that piece of metal or other material is going to determine the resistance. And to take it one step further, we can write Ohm's law, but for fluids. Delta P, the drop in pressure over some vascular bed, is equal to the cardiac output, the flow rate, equivalent to current, times the resistance in the vasculature. Is that clear? This is like the most important concept.
If you happen to know offhand, what are the units of R?
So the commonly used clinical units are Wood's units, and those are, well, if we think about it, we want to get pressure, which is millimeters of mercury, and this is liters per minute. So this has got to be millimeters of mercury per liter. Yeah. And then another. Go ahead.
Does that's ignoring like the Newly effects, etc., right? Where you're having the changing.
Yes.
Like in most systems, you'll have the changing vein or artery size, which will create an energy effect of some sort, I think.
Yes, you're absolutely right. So throughout this talk, we're making a lot of assumptions about flow in the vessels. We're treating all the flow as laminar, and we're also, ignoring like wave reflection and all such effects. The argument there is that we can even do better with simple models that are wrong, like all models, and boost our performance without introducing really computationally intensive models to our work. And so there's also a very important interaction between the nervous system and the heart. And so basically, the autonomic nervous system controls your heart rate. And so you have what's called parasympathetic stimulation, which is controlled by the brainstem via the vagus nerve, which is the longest nerve in the autonomic nervous system. It's just a pointless fact. And so when you have vagal stimulation of the heart, you'll have a decrease in heart rate. And if you have sympathetic stimulation from the sympathetic nervous system, then you'll have an increased heart rate as well as increased contractile force of the heart muscle. And so between these two things, the heart rate is regulated, and actually having a lot of flexibility in this value, a lot of variability in your heart rate is an indication of good health, of having a good, healthy autonomic nervous system. And so in particular, there's two spots on the heart that are stimulated by these nerves. There's the sinoatrial node, which is kind of around here. This is not a particularly good diagram, I guess. And the atrioventricular node, which you can say is over here. And so the heart itself is constructed of muscle cells, cardiomyocytes, which are specialized. And there's some extra specialized ones in the sinoatrial node that fire automatically at a regular rate, which is modulated by the parasympathetic and sympathetic nervous system. You also have the atrioventricular node, which is farther along in the electrical propagation process over the heart, which causes contraction. And it actually functions as a fail-safe for the heart. So if you have, let's say, a bad arrhythmia in the sinoatrial node and you're not having functional contraction, then the atrioventricular node has its own underlying rate. So you can still have ventricular contraction. And the heart has a lot of these safeguards. And so the reason that I discuss this is I want to make the connection between the autonomic nervous system and pressure in the cardiovascular system. So first of all, it relates to pressure because it controls heart rate, but the autonomic nervous system also controls the radius of your vessels, for example, large muscular vessels like the aorta and the pulmonary artery. And as we discussed, this controls the resistance, which in turn affects the pressure. And so this is suggested that there are a variety of measures, kind of like foreshadowing Collin's talk, but there are a variety of measures that are indirectly related to cardiovascular pressures that we might use to discover those pressures. So Now I want to talk about the Windkessel model. This is like, I feel like this is when you study biomedical engineering in your undergrad, this is like, they're a little bit obsessed with it, which is just cool. I support that. It was originally proposed in the context of cardiovascular medicine by Otto Frank, a very famous German physiologist, the same Frank of the Frank-Starling relationship, which says something about contractility and length of volume of the heart. And so to give some background, the original context for the concept of Windkessel, and I don't speak German, but I think that it's a not straightforward word to translate, so we're not going to, but is in a fire engine that's trying to pump water to put out a fire. And so how do you achieve a continuous stream of water, even though you, by design, have to have some kind of regular pumping action? And so this is achieved by having a flexible vessel and having it not empty all the way when it pumps. And that's kind of like a design choice in early fire engines and fire putting out systems. And so you can make a pretty obvious analogy there to the heart, which is it's a pump, it's elastic, and both the aorta and the heart itself, and the heart does not empty completely, the ventricles don't empty completely of blood when they pump. And so what might sound like an inefficiency actually allows you to have regular blood flow, even though you have periodic pumping. And so the way that Otto Frank translated this concept into a quantitative model, which is really his contribution, was via an analogy to a circuit. And so this is just a kind of cartoony diagram of the heart, and we have the aorta here, which has some value called compliance, which is analogous to capacitance in the circuit right there. And compliance is kind of what it sounds like. It's how much does a vessel or any container change shape in response to pressure. So how resistant is it to shape change? So a higher compliance means you're going to have a greater change in volume in response to pressure. And the units are liters per millimeters of mercury or something like that. And then you also have resistance, which we've already kind of argued is analogous to a resistor. And so you can express it as this kind of circuit. And then the voltage drop over here is equivalent to the pressure drop between the left ventricle and actually the vena cava, the vessel that comes into the right atrium. And so we're talking about the pressure drop over your whole systemic vasculature. And so this is the two-element Windkessel model, as the title suggests. It's the simplest version. And there's a couple evolved forms. So the three-element Windkessel model introduces a resistor here to model the resistance of the aorta itself to fluid flow, in addition to the pressure drop over the whole vasculature. And then the four-element Windkessel model adds an inductor here, which basically models the inertia of blood flow. So if you think about how an inductor, it basically adds like a second order term to the differential equation that represents this circuit. And so kind of reflecting the fact that like when you push on blood, it pushes back a little bit. And so we can make a comparison between these models. So this is the impedance, which is like kind of like a summary, a more generic way of saying the resistance when you have non-resistor elements in the circuit, compared to the gray line, which is the measured impedance of aortic blood flow. And then you also have the phase. And so basically what we're seeing here is that, the four-element model, the solid black line, is better than the two-element model, which doesn't really capture the way that the pressure increases again. And then the three-element model captures that, but doesn't capture the shape of the waveform as well. However, we're going to use the two-element model, and here's why. So basically, while the other models capture the shape of the waveform better, the two-element model can, with good accuracy, capture the key clinical values like the mean pressure, the max pressure, and the minimum pressure. And this is kind of the trade-off that you have to think about in this type of work. Do you choose a more complex, more accurate model that's going to be more computationally intensive to solve, or do you choose a simple model that's less accurate? And you know, sometimes simpler models are more generic, and so you can think of that as an advantage. But it's definitely something to play with. And so this expression, this differential equation, is expresses the relationship, expresses this circuit diagram. So you have your capacitance with its first order term and the compliance, or I'm sorry, the resistance, which is, if you look at this piece, it's just Ohm's law. And so Q of T is the flow rate related to the cardiac output, analogous to current in the circuit. And that's going to be some function of time. It's kind of the flow profile in the aorta, because the heart is beating and changing the flow rate locally in time. This R is the vascular resistance, as we said, and C is the arterial compliance. And so we can solve this numerically and also analytically, but because it's a pretty simple differential equation and very stable. You can start at crazy nonsense pressures for your initialization, and it all converges to this nice little waveform, which looks kind of like an aortic pressure tracing. I guess I haven't shown you one of those, so you can't disagree with me, but yeah. And so I want to step through a couple of examples of how changes to the system will affect the pressure. And so consider just this like baseline pressure, which is kind of realistic-ish for an aortic pressure. And so let's consider what happens if we decrease stroke volume. So we're decreasing the volume of blood that the heart ejects on each beat. And so what we see is a decrease in the systolic or max pressure, which makes sense. That the ventricle contains less volume, and so the pressure is lower. And there's also a drop in the diastolic pressure, which, does anyone have an explanation for that? It's not coming to my mind. That's okay. All these things you kind of can like convince yourself why they happened, and then you can also convince yourself the other way, but it's probably wrong. And so now let's consider what I think is an interesting example of what happens if we increase the heart rate. And so basically we can think about two segments in time when we think about the heart rate. We have the duration of systole, or ejection, and the duration of diastole, or filling of the ventricle. And so if the duration of diastole is shorter, then there's less time to fill, and you're not going to achieve as high of a systolic pressure on ejection. If the duration of systole is less, then you have less time to eject volume, and so you're not going to get back down to as low of pressure. So there's going to be less pressure here at the bottom. And we can also consider, these are kind of like the more important examples, if we consider decreasing the resistance. So the vessel is larger, or your vasculature is less resistive, then if we consider our fluid Ohm's law, delta P equals cardiac output times resistance, then having a lower resistance is going to give you a lower pressure. And so we see that here in terms of the max and the minimum pressure. So we can get a similar, actually a little bit larger pulse pressure, which is the difference between the max and the minimum pressure, but the values themselves are lower. And we can also think about decreasing the compliance. And so if a vessel is less compliant, meaning it's stiffer, then you're going to generate more pressure when you fill it with the same volume of fluid. And so I think that's what we see here. During ejection, at max pressure, the pressure was higher. And so this model of resistance, compliance, and pressure drop over some vascular bed can be equivalently applied to the pulmonary circulation. So if we consider the pulmonary artery here, it has some compliance, some resistance to pressure, to changes in volume in response to pressure. And then the pulmonary circulation has some resistance in the same sense that the vascular systemic circulation does. And so we can use the exact same model to model this.
Daphne, I have a question. So
Yes.
I'm not so familiar with the literature, but I'm guessing there's a decent number of animal models that people have looked at over the decades to kind of verify correspondence. And so how thoroughly have these models been explored in terms of correspondence with humans? Because like we were talking about earlier, some of the fundamental physiological parameters you're typically only going to extract in a sick patient, right? You're not going to cath a healthy person. But so can you talk a little bit about the correspondence between these models and human physiology as opposed to, different animal models?
Yeah, so that's a great question. I think that probably the animal model that we're going to see the most for studying this correspondence would be pigs. And the cardiovascular system of the pig is relatively similar to the human cardiovascular system. I actually had the opportunity to participate in a lab where we modulated the cardiovascular parameters of the pig in a HMS class, but which was pretty interesting. But yeah, so the key problem here is that you really are never going to have validation in healthy patients.
Sure.
However, what you can do is you do sometimes have pressure measurements or proxies for pressure in healthy patients, and you can compute these values and kind of think about if they're reasonable.
Right.
I think there's a similar challenge with measuring and studying the autonomic nervous system. And so fundamentally, the autonomic nervous system, and as it relates to the heart, is governed by the firing rate of certain neurons, and there's no way to, ethically measure that in a person, healthy or unhealthy. And so also there we only have animal models and kind of a big analogy to human physiology.
Got it. So I guess maybe that's also one potentially exciting thing about the kind of era of machine learning. If we can infer some of these physiological parameters in a non-invasive way, that opens up the entire frontiers. If you can accurately know what the pulmonary capillary wedge pressure is without actually having to make an invasive measurement, that's not only impactful for sick patients, but it also means we can do better validation of models in healthy patients.
Yeah. So I think that's true. That's definitely like one of the directions of this work. It's a little bit self-limiting because you're using the Windkessel model to validate the Windkessel model, but it's interesting at least to see what kind of results you get and if it's consistent with prior clinical knowledge. Right, so as I said, we have this equivalent representation for the pulmonary circulation. And so here, the blue curve is what you might see in the aorta. Again, it's a Windkessel model, missing a lot of the features of the shape of the waveform. And then the orange curve is what you might see in the pulmonary artery. And so basically, the pulmonary artery has the pulmonary circulation has lower resistance in systemic circulation, because you obviously have much more length in your whole systemic circulation versus your pulmonary circulation. You have a lot more going on there, but the compliance is higher in the pulmonary artery, both because the artery itself is not as stiff as the aorta, and also the small vessels of the pulmonary circulation basically have no muscle tissue. They're just like tiny little capillaries that can change size as much as you want them to within limits. But the stroke volume and the heart rate are the same because it's the same person. And so basically this is completely controlled by resistance and compliance, at least under the assumptions of the Windkessel model. And so now I want to touch on an important example for us in the Stultz lab and in general, which is pulmonary hypertension. Basically, it's explicitly defined as having an elevated pulmonary artery pressure. And so, as we said, that's the pressure right here. And right, and so this is just a pathological image that shows it. You have thickened artery walls, smaller radius, higher resistance. And this is a really large umbrella of disease. There's many different etiologies. You can have genetic causes. You can have what are called you can have idiopathic pulmonary hypertension, which translation, we don't know. And stuff like that. And you can have it as a result of other heart problems. So if you have increased pressure or hypertrophy, enlarged heart tissue on your left side, then you're going to have backup, and that's going to increase the pressure in the pulmonary circulation. And it's also a very serious condition. And so the onset is really gradual. The symptoms are things like shortness of breath and things that you might associate, that you might not necessarily associate with disease, or that you might not notice unless you have other cardiovascular problems. And the median untreated survival is 2 to 3 years. And finally, this disease is completely contraindicated with pregnancy in women. So if basically there's a lot of changes that happen to your cardiovascular system when you're pregnant. And so in particular, consider the fact that the fetal circulation is basically another resistor in parallel with the rest of your systemic circulation. So everything changes. And because of these dynamics, having pulmonary hypertension is incredibly deadly in the context of pregnancy. And so if you don't know that a patient has pulmonary hypertension before they get pregnant, then you have a significant problem. And that's kind of a difficult diagnostic challenge. And to revisit this image, the only way that we can diagnose pulmonary hypertension is through invasive catheterization. So sticking a catheter into your central jugular and down into your heart and up into your pulmonary artery to see if it's greater than or less than 20 millimeters of mercury. So this is obviously really invasive. It's risky for immunocompromised patients. And now in the context of COVID, we could imagine it being concerning for infection control. And finally, it's a highly skilled task, and there's risk associated with it. You can have damage to the heart itself if the catheter punctures anything. You can also have damage to other vessels. And so let's say, I mean, realistically, this is how teaching hospitals work. If a trainee is doing this procedure and not a fellow, the risk might be a little bit higher. And so while it's a necessary procedure, and I'm not telling anyone that it's not safe, that people shouldn't do it, it's invasive and it's suboptimal. And if there were some way to triage pressure without catheterization, then that would be cool. I don't know, maybe there is, we'll see. And so that's it. thank you. Please let me know if you have any questions at all. And that's my email in the corner, so you can email me if you want about this stuff. Yeah, thank you.
Thanks so much, Daphne. So I have a couple more questions about the idea of simple models. There is obviously modeling the heart as an electrical circuit is about the simplest thing that we can do.
Yes.
But even as a kind of a physical pump, it's not totally absurd that we could construct a 3D biophysical model, right, taking into account the stress and strain properties of the muscle and so on and so forth. I'm assuming there's some literature on that level of detail. Can you talk at all about what is lost when we don't model the heart kind of in all of its 3D glory? I mean, even modeling the heart as a kind of non-biological pump that has the geometry that it has seems to have substantially more complexity than the simple electrical circuit model. And I do wonder, with all of the different imaging modalities we have these days, might we in 5 to 10 years be building biophysical models of everybody's heart and moving beyond the Windkessel model?
Absolutely. So definitely with things like cardiac MRI now, you can construct beautiful 3D representations of the heart. And what I would argue about the simple models, Windkessel in particular, maybe I'll stop showing my slides, by the way. About Windkessel in particular is that the concept of bulk resistance across a vascular bed and compliance of an artery, while it's technically a model, it is kind of fundamentally descriptive. And kind of the function of models is that, like, we know how these quantities relate to clinical reality. And I think that things like having a more detailed, more accurate mechanistic model of the heart as a pump is interesting, because you definitely have the potential to discover new biomarkers, for example. And if you're thinking about more detailed circulatory problems, like, for example, if you're looking at the coronary arteries and you want to know what happens if there's occlusion to n degree in X branch of the coronaries, then you want a more complex fluid dynamics model than a circuit. It really depends, I think, on the application, right? I think for pulmonary hypertension, considering current clinical approaches, inferring, for example, the resistance without a cath is pretty informative. Something else, one thing that I do know about, which is a little bit different from the fluid dynamic modeling, there are a lot of really interesting models for the electrical activity in the heart and how the action potential propagates. And so if you have some tissue, some muscle tissue that's dead or damaged, it will affect the wavefront and creates these like curled wave patterns in the heart. And that type of thing can be guided to you for something like an ablation procedure to get rid of these faulty cells and allow for more healthy, normal contraction. And so I think there's an analogy there to the detailed biophysical models. If you wanted to, for example, do some kind of procedure, do some kind of either place a stent or do a valve replacement, and you want to see how is this really going to change in detail this person's dynamics, you're not necessarily going to capture that in the Windkessel model, but you could capture something like that with the biophysical model. And so I think it depends. Like I said, it depends on the application. You kind of have to choose the right fit. You have to think about how much time you have. So with Windkessel, we're thinking about triage and early detection. So you want to keep it simple. But then when you're thinking about, let's say, preparing for a surgery, you're going to take a cardiac MRI and you're going to generate this complex model.
So practically, looking at the direction that compute resources are going in, right? Everything is being driven by machine learning. What do the compute requirements look like for a biophysical model of the heart, right? Given that these tend to be, right? I mean, like simulating a ODE or a PDE is a very different thing than training a neural network. So if we imagine a future where everybody has a biophysical model of their heart, is that consistent with what's going on in cloud computing, or is that the compute requirements look very different for simulating these detailed models?
So I don't have a very informed answer to that question, but I can, I guess. I think it's probably somewhat feasible. As I understand it, these types of simulations, if done in a purely mechanistic way without any machine learning or anything, are pretty expensive, take a long time. I know that, I don't remember the paper, but there was some work to kind of simulate the hemodynamics of the whole cardiovascular system in all vessels and the flow and the fluid dynamics in detail, and it takes like days and days and days to simulate. It's like,
Got it.
it's like nonsensical, not nonsensical, but it's like, it's very, very expensive.
Sure.
And so, yeah, I don't have like a numerical answer.
No, that's okay. That's helpful. I was just, this is something that's in the back of my mind a lot because, you know, there are these huge industrial pressures, right, that are making certain types of compute accessible because that is what the tech industry needs. And I think that in an ideal world, if healthcare and medicine were driving these things, the national IT infrastructure might look a little bit different. And so I kind of wonder how things will unfold given the resources that we do have at our disposal. Mike, I think you had a question.
Sorry.
Yeah.
Sorry, could I just, sorry to interrupt there. My name's Brody. I'm a postdoc at HMS, but I actually do a lot of this large-scale biophysical simulations of blood flow in the pulmonary system. So just quickly add, as like a rough estimate on a home computer using a GPU, if you wanted to simulate, let's say, 100,000 branches, you'd probably be looking at like on the order of hours to simulate seconds of blood flow if you're trying to do it at like doing pressure gradients, Navier-Stokes only in 1D as well, because I haven't really seen any work that's done beyond 1D if you're getting into really large systems. So it is becoming more accessible, but it's still a long way away, particularly the further you get down, because as you get into the smaller veins and arteries, you have to start accounting for different properties of blood flow as well, that the Newtonian fluid kind of assumption breaks down. Sorry to interrupt there.
No, thank you. That's very helpful to know.
That was really cool. I had a quick question, which might be, I'd just be curious to get your intuition for this if you have any. It was asked earlier about kind of generalization to healthy patients and to what extent you can take some of these models maybe developed and kind of validated on the people who actually receive these types of actually have these invasive measurements taken. And I guess I'm curious, like, is your intuition, where does your intuition lie on the extremes from, on the one end, like the hearts of these patients are totally different than healthy hearts, and therefore you're kind of extrapolating to healthy people? Or on the other extreme, there's so much variation that within the types of people who have these measurements taken, you can find some hearts, I suppose, that look like what you'd expect a heart to look like in a healthy patient.
So from my own experience, looking at the data that we have, the hearts of patients who get catheterization, for example, look pretty different from healthy patients. And the distribution of their pressures and their resistances and other values are definitely pathological. I guess my main thought about this is that when we introduce a mechanistic model that's based on some like prior knowledge of physiology, that physiology applies to healthy and to sick people, right? So like this circuit analogy of the heart, however accurate or inaccurate it is, and it's very inaccurate, is equally applicable to healthy people and to sick people. The concept of pressure drop over the pulmonary circulation is equivalent in these two. So I actually hope that models like these can help generalize to healthy patients, if that makes sense.
Daphne, just so I understand what you're saying, to clarify, the kind of philosophical point about models aside, you're saying the basic assumptions of models aren't undermined by disease states, right? So somebody that has a sick heart, like it's not that the tissue isn't so damaged that we can't use these models anymore?
I mean, it depends on the specific case, but you want to choose a model where the diseased heart has different parameters, but not a different actual model.
Yeah.
Then
you're in a different parameter regime, not a totally different model.
Exactly. Alternatively, many people argue that you should train different models for different subsets of patients, and so maybe there's some analogy there in mechanistic modeling.
I guess
oh, sorry. Go ahead, Michael. I'll go after you.
As a follow-up to that, it seems like the argument is, if we really model the mechanisms correctly, then you can change the parameters to values you maybe haven't seen as much of before, but that everything will still generalize if the mechanistic model is correct, because that's kind of the underlying ground truth.
It isn't.
No, and I understand. You're not claiming
it
that.
Never will be.
I guess that's my follow-up question, which is there room to, just because we were talking about simulation before with like really intensive compute, it seems like you might see within your cohort of patients that my simple model does a pretty good job, but because I know it's inaccurate, maybe I don't know how well it'll extrapolate really far outside of those types of patients. But is there work on kind of comparing, I don't know if this question even makes sense, like how well it extrapolates when compared against like really detailed simulations of healthy patients, or even just like how much predictions might diverge for healthy patients between like simple and like more complex mechanistic models?
Yeah, I mean, so there's work studying like the different levels of complexity of the Windkessel model, which are all still very simple. I'm not familiar specifically with work comparing complex biophysical models or fluid dynamic models with Windkessel. I think, as Brody mentioned, it's hard to get long-term projections from those kinds of models. And yeah, I guess our alternative approach to kind of like addressing the wrongness of these models is to bring it together with some statistical models.
Cool.
Hey,
A lot of that work in lungs as well. If you like the similar Windkessel resistance stuff in airflow, and that's been more directly validated at different stages of 1 compartment models, 7 compartment models, 1,000 compartment models, particularly the work of Sylvia Verbank. And it broad takeaway seems to be certain types of disease, the simple models extrapolate extraordinarily well. Other types of disease, they don't. Depends on the kind of mechanistic damage you're trying to simulate, ...
Thank you.
Hey, Daphne, this is Eric. I have a question that's a little bit broader. Well, first of all, fantastic overview. I think it was really interesting and informative. So my question is, we've looked a lot at this intersection of computational modeling with machine learning, and in the diverse landscape of problems to attack, disease states to understand, apps to build, where do you think the low-hanging fruit is? Like, what are the most interesting areas to focus on at that intersection in the next few years?
I'm a little biased, but I think that cardiovascular medicine is a great place to look at this intersection, because I think our mechanistic understanding of the heart and the cardiovascular system is pretty good. For example, if we wanted to think about like, what would we do like with the brain? How would we combine a mechanistic model with the brain with machine learning? I think that would be a little bit more limited because we don't have extensive models describing, neurological function. Similarly, you can start looking at like renal function, because that's also kind of a hemodynamic problem. Yeah, I mean, I think that I don't necessarily have a vision for how to bring this into the world of like cells and cellular models, but I think because it's not really, I don't have a lot of background there, but I think that's also going to be another direction.
I'm going to try to discuss how physiology can inform the design and interpretation of machine learning models for predicting adverse cardiovascular outcomes. I think the previous discussion was very enlightening, especially the questions. And there are some of you that have expertise in complex modeling of different organ systems. And I want to begin this colloquy by saying that our focus is really aimed at clinically motivated questions. And so the types of models that we do and the sorts of questions, what makes an appropriate model for us is dictated always by the clinical need. One of the strengths of the Windkessel and some of the things that Daphne talked about is these lump parameter models capture large features that have clinical significance. Very detailed models can be much more accurate and of interest to understanding the underlying physiology, but whether they're really useful for understanding the big picture clinical questions that plague most patients is not clear. So I just want to use that as a proviso for moving forward. So I like to begin these sorts of talks with the following. And many of you have seen like maybe the first few slides before, but I think it's useful just to show them again so that we're all speaking the same language and coming from the same background. So the holy grail of much of medicine, cardiovascular medicine in particular, is to take data that there's my PowerPoint. Where's my, oops, sorry. I'm trying to get at my, there we go. So one of the things that's useful, we want to incorporate data coming from multiple sources from a patient. And the promise of machine learning is that it can integrate lots of data, lots of information that we as clinicians can't really think about. We have to prioritize the different types of data that are acquired, especially in the intensive care unit setting, to be able to make clinically useful inferences and decision making. And the promise of machine learning is it can integrate all of these types of data, much of it that we can't process, to do useful things for the patient, like minimize the length of stay, readmission rates, complications, and inform clinical management decisions. Now, while machine learning in healthcare sphere has been widely recognized as being useful, it has not been embraced by the clinical community. And I think this is especially true for complex algorithms that take different sources of data, lab data, physiologic signals, clinical notes to derive some sort of clinical prediction and or recommendation. And so we've said this, other people have said this as well as to why this is the case. Well, a lot of these models are very complex. Many of the deep learning models that especially some of the people here have listening to this talk have developed are very complex, very hard to understand, and it's really hard for any clinician, indeed any lay person, to understand what these models have learned, and consequently to have some faith that they're doing something that is reasonable. This black box approach makes it difficult, in particular for the clinician who really has to make informed decisions for a particular patient. And as long as the model is not 100% accurate, there's a chance that it could be incorrect for a given patient, and it being incorrect can be very disastrous for a patient, especially like if you're predicting interventions that might save someone's life who's at high risk of death, and the model incorrectly predicts that that patient is at a low risk of death, and you've missed an opportunity to save a life, to prolong life through appropriate medical therapy. So another way of saying the same thing is determining whether a model is useful for clinical use. In the literature, typically involves evaluating the model's performance on a large patient data set using standard statistical measures of success. So there's accuracy, discriminatory ability, lots of things that statisticians opine about for quite some time. But however, in the healthcare sphere, accuracy does not, and I would argue, nor should it, ensure that the model will gain clinical significance, precisely for the reasons that have already been talked about. if the model is less than 100% accurate, one needs some way to be able to justify to him or herself that the model is going to do something good for their patient. So how do clinicians think about evaluating machine learning models? So they've got this black box that takes inputs and does stuff that is very complicated to comprehend. And the clinician has to, try to decipher whether this is appropriate for his or her patient. So one question is, even though the overall performance of the model is good, it's evaluated on some data set of patients, will it work for the specific patient that the clinician is interested in making clinical decisions about? So moreover, is the model consistent with what the clinician knows about human disease? So as I've said to some of you previously, first medical school was well over 2 centuries ago. I think it was 270 years ago. And in that time frame, we've developed quite a large collection of clinical observations and data. And any machine learning model is trained on some subset of patients, no matter how large that subset of patients is. It pales in comparison to the experience to the patients that have been cataloged and experienced for the last few centuries. So to be certain this model will be broadly applicable and generalizable, it's useful to say that it's consistent with this large panoply of data that exists in the medical literature. And lastly, the most hardest thing to get across or to sort of for anyone to understand, myself included, is really what has this complicated model learned at the end of the day. And that's a hard question. And I tend to categorize these things into 3 different categories. So there's trust being the first part of this. Even though the model has an overall performance which is good, will it work for my particular patient? Can I trust that this model is applicable for a given patient? Consistency. So is this model consistent with what I already know about human disease? And lastly, something very nebulous called explainability, right? What has this model learned? So because I can't see anyone, I just want to make sure that people are still there and I still have a connection with everyone.
Hi, Collin, this is great.
Okay, all right, good. I just because I just want to make sure I don't lose you, and I'm just talking to our cats or.
No, the audio and slides are both great, Collin.
Okay, all right, good.
Yeah, you got 77 people following along. So.
Okay, all right, good. Okay, excellent. So these 3 broad categories, and I'm not going to talk about each of them separately today. I'm just going to focus on one of them, this strange notion of explainability. And I want to try to convince you that what the clinician means by the word explainability, what he or she means by an explainable model. And if you have something that is explainable, then you can devise methods to design explainable models that make trust and consistency a corollary or of whatever explainable formalism you have. I hope to make that clear in the next few slides. So explainability, just as a background. So what does explainability mean? So we have a machine learning class at MIT, more than one machine learning class at MIT, but one that's taught within ECS references this paper. I have graduate students come to me and say, well, explainability. And everyone mentions about the Zachary Lipton paper published in the Association for Computing Machine, ACM, some time ago, that tries to talk about interpretability and or explainability, where those terms are used somewhat synonymously. So there are these criteria that are laid out. It has to be transparent, simulated, this notion called simulatability. And parenthetically, I don't think any of these are actually words in the English dictionary. I tried to look up explainability once and didn't come up with anything. There are things online about what explainability, but whether it actually is a word or not, I'm not sure. Anyway, so there's decomposability, that each part of the model admits to an intuitive explanation. These are really hard criteria to meet for any model to classify it as being explainable and or interpretable. Having said that, though, there have been a lot of approaches that try to do this generally. So you design some complicated deep learning model, and then you want to try to hint at something that's explainable, and there are these methods that go with text explanations, visualization, local explanations. We won't get into any of those. And I think part of the problem with these is that these are methods that are devised to be quite general, to be applicable for any model in any application. And I think those who develop these methods say that, use applications from many different domains to try to illustrate how they lead to some explanations. And that's really, really hard. And explanation, in my view, is a function and part of the domain in which the model is used. So I'm going to restrict this discussion to explainability in a clinical context and what it really means. So machine learning model explanations, just filling in on these later things that have been developed for many classes of problems that have been applied to clinical problems. There's things that I'm sure a lot of people here are familiar with: gradient weight class activation maps, GradCam, Shapley values, saliency values. And they just largely tell you about input features that are most important or most discriminative for the model to arrive at particular. So you get some insight into that particular question, but does that really mean what explainable means? So this is kind of a philosophical question, but if I give you a list of input features in a model and I say, well, these features are important, have I really explained what the model is doing? I'm not sure. And moreover, these methods can be a little misleading because they focus on specific areas, let's say, of an image, and they may say these particular pixels have the most discriminative power, and it leads one to ignore the other pixels in the image that may be contributing. And I don't think that's a favorable consequence of this. So there are a host of other methods that purport to do the following. So you have some very complicated model, which here is depicted on top. And then you want to create some other model that is an explainable model, very easy to understand, maybe a decision tree, maybe a logistic regression, that sort of does the same sort of thing that the model does, and it sort of represents an explanation. Now, these approaches, I think, have merit, but I want to refer to Cynthia Rutan at Duke, who has, I share her view here. In terms of these class of models. And so this is taken from her paper, Stop Explaining Black Box Models for High Stakes Decisions. And if the explanation, meaning if the explainable model was completely faithful to what the original model computed, the explanation would equal the original model, and one would not need the original model in the first place, only the explanation. In other words, this case where the original model would be interpretable. So one can aspire to do this, but the explainable model must necessarily miss something that this very complicated model encodes, because if it didn't, you would have used the explainable model in the first place. So post hoc explanations of complicated models, I think, are really difficult to understand and or justify. So it's interesting to sort of I think we should take a step back and look at really what the word explainable means, and in particular in a clinical context. So the previous, whatever explainability means, it has to be considered when building the model rather than post hoc, and I think for the reasons that were articulated on the previous slide. Now, explanations are inherently subjective and can differ from specialty to specialty. So an explanation to a neurologist may be, that a neurologist may find satisfactory. It may sound like Swahili to me as a cardiologist. So notions of explainability has to have in it some understanding or appreciation for who the listener is, who the audience is that you want to convince. So this makes it challenging to arrive at an objective definition of an explanation, especially for clinical problems. So let's just take a common sense approach to an explainable model. We can define necessary conditions for a good explanation. So what do I mean by that? First thing, an explanation encompasses a discussion where all participants speak the same language. If there's some cardiovascular anomaly that I wish to understand, and someone else does understand it, they have to explain it to me in terms that I am used to hearing as a cardiologist, that are consistent with what I have learned in medical school, what I have learned through the practice of cardiology. So explanations for models that are intended to be used in a clinical context should be worded in a language that is familiar to the clinician. And physiology in general provides a lexicon for doing that. In medical school, clinicians all take physiology courses in different types of physiology, respiratory or renal or cardiovascular, and they carry this lexicon with them into their clinical practice. And I think this is one of the reasons that Daphne gave a very astute and polished presentation. I think that sort of try to explain some of these terms and concepts that clinicians carry with them as they see patients and as they think about human disease. So in light of that, what is a metric of success for model explanation? When is an explanation for model presented and one goes, yes, I understand it, that is a good explanation? Satisfactory explanations are intuitively subjective, and an explanation is successful if the audience understands it. Now, as a sentence in and of itself, this is not very informative, but I do think that it has an appeal to it that I think everyone can appreciate. Everyone has that light bulb moment when someone explains a concept to them and they get, I get it. And more specifically, I think a clinically useful explanation leverages this physiological lexicon to justify why a particular prediction was made. So in my view, a successful explanation uses this language that all clinicians rely upon to think about human disease and think patients in general. So in evaluating a machine learning model, I'm not going to talk about trust and consistency, but really this explainability, which again is providing supporting evidence using a lexicon that is similar, that is familiar to the clinician in particular. And for this talk, this lexicon arises from physiology. And that's going to be the focus here. If one does that, if one can arrive at a robust physiologic explanation, then trust and consistency automatically follow. So for example, in the case here, I have a patient and his or her data is being supplied to this deep neural network that is this black box that does things that's very hard to understand. And let's say the model predicts that this patient is at high risk of cardiovascular death. If I can get my pointer again. Yes, at high risk of cardiovascular death. Then, let's say I had some translator that took this and tried to express some supporting information in physiologic terms. So for example, using terms that Daphne introduced, this patient has a low cardiac output, has the elevated left atrial and diastolic pressure. So the pressures within the heart are elevated, and it's all consistent with a dilated cardiomyopathy. Well, that makes sense. Higher risk of cardiovascular death. In these types of patients, I would expect them to be sort of in a low flow state generally. So, this is consistent with my prior information, and it leads me to have some trust in what the model is telling me. By contrast, so if we have the same patient with the same set of features input to a model, and the model predicted a low risk of cardiovascular death, and I looked at my translator and it said, again, there's a low cardiac output, dilated cardiomyopathy. This is inconsistent. I wouldn't expect someone at a low risk of cardiovascular death to have a dilated cardiomyopathy. And in this instance, because supporting evidence that's provided is inconsistent with the model prediction, I'm going to ignore the model. I'm going to lead to distrust because it is inconsistent, internally inconsistent, inconsistent with what I know, in a sense, inconsistent with what I know about the pathophysiology of disease. So we have trust, consistency, explainability, but really what's important here are these robust explanations that are grounded in human physiology. And because explainability is a word that has such a long history within machine learning, and I think that the hardcore computer scientist aspires to develop methods for explainability that are applicable across domains. I want to absolve ourselves from these prior notions and talk about, use another term, we've got to call it justifiable. And you know, there are sort of justifiable machine learning models. I understand there's some literature here, but the hope here is to sort of divorce this notion of justifiability for the clinical machine learning models from what has been published previously. So now I'm going to try to give an example of some of these notions. But before I do, again, because I can't see everyone, and it's not clear to me whether everyone has drifted off into REM sleep or not. Were there any questions thus far, or are people still with me?
Yeah, the audio and slides are coming through great, Collin. Collin, just kind of one thought. I'm curious for your feedback on it. You know, so in my medical school, our pre-clinical curriculum was organized around organ systems. And I spent some time digging into the history because I thought this was an interesting way of structuring the curriculum. And I think it's a big trend nationally. Like, medical curriculum wasn't always organized around organ systems. My understanding is, if we go back a few decades, it was more kind of traditional biological topics like cell biology, histology, or immunology. And I think this natural trend towards teaching in organ system blocks like the cardiovascular system, the nervous system, really reflects the mental models of how physicians think. And so one of my takeaway from that experience was that this really gives us a natural abstraction for how we should think about organizing machine learning models, particularly from the standpoint of what you're calling justifiability, right? I mean, there are...
So Gopal, this is Gopal, right?
Yeah, this is Gopal, Collin.
You're a physicist, right?
Yes, that's right.
Okay, I knew I liked you. Yeah. So right. I think that's absolutely correct. The only proviso I would say is that the organ systems, I think, were a part of clinical training, but it wasn't divided into blocks. It was there, but it wasn't divided. And I think I'm echoing the same thing that you're saying. And I agree with you wholeheartedly. And I think that we should try to, I think that the future of these models in the clinical space is going to be thinking about them and using that information in the design of these models.
Absolutely.
Okay, so I'm going to try to give an example of some of these concepts. And Daphne already talked about pulmonary arterial hypertension. And actually, I shouldn't have this word arterial here. I really, you'll see why in a minute. I really just want to talk about pulmonary hypertension. And I want to talk about detecting pulmonary hypertension from the ECG alone. And this is work in progress. So this is not work that has all of the, I's dotted and the T's crossed, but I thought it's an interesting way to think about the application of some of these things. So if you'll indulge me, we can talk about sort of the work and the progress thus far. And I have to say, sort of before I begin, a lot of the work that I'm talking about now was done by Daphne Schlesinger, Nate. Is Nathaniel there? No? Okay. Well, kudos to Nathaniel, who actually did.
He's here.
Oh, he's here.
Hey.
Who actually did a lot of this work as well. And I should say this work was also facilitated greatly by Eric Reiderson and Stephen Song, who mainly Eric, who did a lot of work in sort of getting the electrocardiographic data, and ML4 CVD group, so that we could do something useful with it. So what is pulmonary hypertension? So pulmonary hypertension is a disorder that Daphne described where pressures within the pulmonary vasculature is elevated. Now that's a very physiologic definition, albeit accurate, not very useful for the patient. So more accurately, and I think this is something that Daphne brought up as well, patients with pulmonary hypertension usually present with shortness of breath on exertion and fatigue that progresses over time. And as Daphne alluded to, the diagnosis is often delayed because these presenting signs and symptoms are often attributed to age, deconditioning, or other sorts of medical conditions. So these patients can present quite late. And left untreated, it has a quite high mortality. So the 5-year mortality for one particular type of pulmonary hypertension is greater than 40% in some registries. So it can be a quite lethal disorder. Now, how is pulmonary hypertension diagnosed? So the gold standard is a right heart catheterization. Again, just to echo some of the points that Daphne made. So it's an invasive procedure that entails threading a catheter into one of the great veins. Here, a catheter goes into the internal jugular, goes into the heart. There's a right atrium and the right ventricle. It goes out into the pulmonary artery. We can measure pressures. There are many places nowadays where we can put the, we don't have to do the internal jugular. It can be the subclavian vein, the brachial, but basilic vein, brachial. So, the point of entry is not important. What is important is it goes in through a major vein, goes into the heart and into the pulmonary vasculature. So consequently, it does require some expertise in placement and is subject to complications, especially in the hands of those with little experience. How else? So that's the gold standard. How else can you diagnose it? Well, there's cardiac ultrasound. So cardiac ultrasound, you have an ultrasound probe, you put it on the chest, you can measure, you can take a look at the pumping function of the heart, and you can take a look at the velocity of blood as it goes through the right heart. And the velocity of blood is related to the pressure in the right ventricle, more precisely the pressure gradient between the right ventricle and the right atrium. But the point is, you can use those velocities using by measuring Doppler, the velocity of the red blood cells that are in the right ventricle as they go across the tricuspid valve to estimate the PA, the pulmonary arterial pressure. Now, the problem here is that it requires expertise in sonography. At MGH, there are sonographers who are full-time employees, and all they do is they do these studies. And you really need a good one to get a lot of information, in particular because for lots of patients, getting the right angle and the view can be challenging. Now, even when you can do that, translating that velocity to a pressure within a pulmonary artery it requires some assumptions. It's a physical model involved, and one has to make some approximations to be able to translate that to a PA pressure. And you have to make some approximations what the baseline pressure is in the right atrium. So approximations are needed and expertise are needed with respect to sonography. So an easy to implement method for identifying pulmonary hypertension, in our view, would facilitate finding those patients who are high at risk and getting to therapy early, specifically because, as mentioned previously, a lot of these patients present very late because pulmonary hypertension is not considered early enough as part of the diagnosis. So we have a hypothesis that the electrocardiogram contains information that can be used to identify patients with pulmonary hypertension. Now, using the electrocardiogram for pulmonary artery pressure estimation, because again, pulmonary hypertension means elevated pressures in the pulmonary arteries. And why would anyone expect the ECG to have any information related to pressure in the pulmonary artery? So I say that because when you think about the ECG, it really measures, it really tells you about current flow through the heart. And what does current flow in the heart have to do with the pulmonary? So it's not obvious that this should be true, but to provide some motivating factors for I think Patrick Eleanor is here and Steve Lubitz are listening. So before they, the specialists boo-hoo this, boo-hoo, I don't know if boo-hoo is the right word, but dismiss this, I thought I would sort of give a little bit of a motivation here. So it is known that long-term ECG is useful for looking at proxies of the autonomic nervous system. So there is a quantity called heart rate variability, and there are a number of metrics that are used to calculate it. And at its core, it measures variations in the heart rate over time. And it has been shown from experiments with animals where you can get a more quantitative sense of the relative amounts of sympathetic and parasympathetic stimulation, that it's related to that. And the autonomic tone, the relative amounts of sympathetic and parasympathetic tone affect the pulmonary arterial pressure. In fact, they affect the lead blood pressure, they affect arterial resistance, it affects heart rate and cardiac output. So you could think about the ECG in some way by encoding some information about the nervous system And because the nervous system affects the pulmonary arterial pressure, it's not so crazy to think that these things would be related. And just to drive this point home, even for short-term ECGs, this is useful. So Daphne, for example, calculated some HRV metrics. So these are quantitative numbers that are intended to capture the, in some sense, the autonomic tone, and use those to predict the pulmonary arterial pressure in a particular cohort. And the associated AUC is not great. It's about 0.6, but I'm kind of, was initially surprised that it was as good as it was. So HRV, calculated for something as small as a 10-second ECG tracing, weakly discriminates between patients that have and the patients that have pulmonary hypertension, patients do not. So I think that's one motivation. That was the initial motivation for using the ECG for estimating the pulmonary arterial pressure. Moreover, for chronic pulmonary hypertension, there are well-established structural changes in the heart that are different in terms of just the shape of the ECG, the shapes of different beats that are characteristic, well, not pathognomonic, but characteristic of patients that have long-standing pulmonary hypertension. So using this as a basis, we took a supervised machine learning approach here. So we had to take a data set of patients who've had a cardiac catheterization, the gold standard, who had a measurement of PA pressures. And we had ECGs from those patients where the ECGs were acquired in close proximity to the time at which the catheterization was done. And we want to learn a deep neural network that learns the relationship between the ECG and the PA pressure. So standard supervised learning with a deep neural network, nothing fancy here. However, all steps in the process are guided by our intuition of the underlying physiology, as I hope to explain. So, what data sets did we have to bring to bear? So, Eugene Pomerantz at Mass General is very kind. We wrote an IRB and got access to a data set of patients at Mass General over several years that have had cardiac catheterizations, and there are a total of about 12,000, a little over 12,000 patients. 12,000 patients in this cohort who had a cardiac catheterization for a variety of different indications. It's an observational data set, which is again a limitation here, but I hope to touch on a little bit later. So a lot of these patients were admitted with heart failure. Some of them had an acute coronary syndrome, coronary artery disease, but they all had pulmonary arterial pressures measured. From this cohort, 4,693 had ECGs the same day as a catheterization. So it's from this set that we really want to use for our studies. However, only 3,141 of them had a complete set of hemodynamic measurements. So pulmonary arterial pressures as well as other pressures in the right side of the heart. And all of these data we want to exploit. So what we did here is, given this, we wanted to approach this sort of as a transfer learning problem. We could look at a larger data set and we could try to extract representations of the ECG that might be useful for the specific task of predicting the PA pressure from the ECG. So we have a pre-training data set. That's 270,000 total ECGs from MGH, all sampled at 500 hertz. And this is heroic work done by Nate in this for the pre-training here. So the data set for the pre-training, again, there are about 276,000 patients. All of them had 12 leads, and it's 10 seconds for each lead. We also have, for ECGs, we also have information about the age for each patient. We divided this into training, validation, and testing set. You can see just the mean age and the heart rates and PR intervals and such for these patients, just to convince you that this is not an outrageous data set, and it may be quite similar to the range of things that we see in patients clinically every day. So then we constructed, I should say Nate constructed, a convolutional neural network to abstract high-level features from the ECG. And surprisingly, the network that worked well is actually quite simple. So you start out with the ECG, and you just have sort of a simple CNN. It's got 30 convolutional channels. The width is fixed at 16. And there's a swish activation. As you know, switch is sort of a continuous version of ReLU. And then from there, we did some max pooling, multiple rounds of max pooling, followed by dense blocks, and finally flattening it. I think it was like 512 nodes. And then there's a fully connected layer. So what ends up here at the end of this fully connected layer is some latent space, and it's the size of the fully connected layer that determines the dimensionality of the final latent representation that you have for the ECG. Now, what was the pre-training task? Well, we know that from what I showed you previously in the work that Daphne did, is that the heart rate variability metrics are weakly discriminative with respect to those who have patients who have pulmonary hypertension and those who do not. I see I may be running a little over time, so I will try to I will try to cut this short. So so we want to use this to predict variables that are used to calculate heart rate variability, because heart rate variability is changing heart rate over time. So Nate tried to regress the heart rate, QRS interval, PR, QT interval, and the model actually works quite well. So these are all Pearson correlation coefficients, and they're all above 0.94. QRS, they range from about 0.94 to almost 1. And I think these data were generated with a latent space that was the size of 224 nodes. So we have a model that we think we can pre-train well for a task to predict these variables that are related to heart rate variability. So standard transfer learning, we cut off a part of the model that ends up in this latent representation after it's been training. And then Daphne took this part and she added some additional layers at the end to an output layer for a new task. Now, the simple solution here would be to take this output layer and just have it output the pulmonary artery pressure that we have from about 3,000 or so patients in this Apollo data set. But we did a little bit more than that. We used the model to predict more than one output. So there's a pulmonary arterial pressure. Oops. The pulmonary arterial pressure. Let's do this again. So there's a pulmonary arterial pressure, something called the pulmonary capillary wedge pressure. All of these measurements are down there. The cardiac output and the pulmonary vascular resistance. We've already talked about the pulmonary arterial pressure. Daphne mentioned about the pulmonary vascular resistance and cardiac output. The wedge pressure is really just a left atrial pressure. So it's pressure in a different region of the heart, a left-sided pressure. So why? Because the evaluation of patients with pulmonary hypertension entails not only their PA pressure defines what their pulmonary hypertension, but the value of these other clinically meaningful variables that are useful in understanding the etiology of the pulmonary hypertension. So we wanted to predict all of them. So in practice, we predicted the pulmonary arterial pressure and all these other components, and we did this in a binarized way. We initially just tried to regress on the 3,000, but that didn't work very well, I think because we have just too small a data set. So we binarized the pulmonary arterial pressure by 20 millimeters of mercury. That's sort of the cutoff, and wedge also by 12 millimeters of mercury. That's the cutoff for the upper and the lower limit of normal. Similarly, the cardiac output and the PVR to 3 Woods units. So when you do this, the AUC, just looking at the pulmonary arterial pressure prediction in a test set is quite good. It's about 0.78.
Collin,
yes.
Just a quick question, sorry. Did you binarize so that you could look at the AUCs, or are these like very clinically relevant thresholds and that's why you binarize?
Good question. So we binarize, so these are clinically meaningful thresholds. So the definition of pulmonary hypertension is when the PA pressure is above 20. 12 is the upper limit of normal for the wedge pressure. Cardiac output of 4 is a lower limit of normal, and 3 Woods units is the upper limit of normal. So the binarization was done based from for clinical reasons. Ideally, you'd like to be able to regress, and you'd like to be able to estimate precisely what the pulmonary pressure is rather than whether it's above or below 20. But the data set wasn't big enough to be able to regress the precise value. So then we did, the second step was, well, what are clinically meaningful cutoffs, and use that to binarize the data. Does that make sense?
Yeah, that makes a lot of sense.
Okay. So when you binarize it,
and I could just say one more thing. I think it says in the schedule that it only goes until 11:45, but you do have until the hour, so I don't want you to feel like you have to rush.
Oh, okay, all right. But
we just kind of merge into the discussion after this anyway, so you really have until the end of the hour if you want.
Okay, great. Okay, thanks. I will try not to be verbose. I am shocked that I have not made one joke about the debate last night. I have not been able to stop thinking about it.
It's tough.
But I got 10 minutes left. So, right. So if you look at the AUC, so, it's interesting when you look at the literature for, predicting images, image classification side, ridiculously high AUCs. But for clinically meaningful problems where, we don't have these very powerful feature sets, if you look at the AUCs of most things that are used in clinical practice, about 0.7, some of them are between 0.65 and 0.7. Very few of them are, at least in my understanding, about 0.75 or greater. And so I think this is really on par with the metrics that have entered into clinical care, or even better, I should say, than what's used, what's been done. And this is an average over 10 separate bootstraps.
Collin, I'm sorry, when you're comparing them to existing models that are used in clinical care, can you give examples? What exactly are those?
Yeah, but these are not models for predicting pulmonary arterial pressure. So I meant just like clinically. So for example, there are metrics we use to predict risk after certain things, like an acute coronary syndrome, the risk of AFib, and those are the AUCs I mean. They're separate problems, but clinically, those are the AUCs that have entered, in which models that we use clinically.
Got it. Thank you.
Sure.
Collin, this is Eric. I had one other question, somewhat related. So my understanding is that this model is solely using ECG voltage for the input, which is really interesting because clinically, when you think about pulmonary artery hypertension, there's a suite of other risk factors like demographics and pre-existing conditions. In your view, do you think there would be any utility for incorporating those other variables in a model?
Absolutely, 100%. And I think that the next phase of this would be to include those other variables, as you say. I think it is an intellectually interesting question to ask, just how much information is there in the ECG alone for doing this? Because we started with this HRV sort of, relationship with this, autonomic tone within the ECG. So I think that's the motivation for this work. But I think if one wants something that's really clinically useful, it would use all of the available information, which some of those demographics, possibly lab values, prior medical history would be very apropos. Does that answer your question, Eric?
Yes, thank you.
Okay, good. So now, so we have a good AUC, and we could, in the spirit of standard machine learning, well, we've trained a deep neural network. It has this predictive ability, and we could sit back, have our Belgian beer, and just relax and call it a day. However, that's really not enough. And in keeping with the first half of the talk, in terms of other things that we thought were useful and made a clinically useful model. So let's see what about the other things that we've calculated. So we know that not only do we estimate, albeit in a binarized form, the pulmonary arterial pressure, we also had the cardiac output, the pulmonary vascular resistance, and the pulmonary capillary wedge pressure. So these quantities are directly related in this relationship. So when you do your cath, you would expect the mean pulmonary arterial pressure to release the mean cardiac output times the mean pulmonary vascular resistance plus the pulmonary capillary wedge pressure. So you could think about the model in reality predicts the pulmonary pressure in two ways. One, it predicts it directly from the ECG, and one, it predicts these other components that you could use to calculate the pulmonary arterial pressure. So what we can say is, well, we have these four different, and we haven't told the model anything about this underlying physiological relationship between these four variables. We said just predict the four of them. So we can look at the predictions from the model, and we can see, well, when these predictions agree, when this relationship holds true, then we're going to say, okay, the model really captured something about the underlying physiology, and we're going to trust the result. So to make all of this precise, we're going to create an unreliability score. So the unreliability score uses the three model outputs, which is the cardiac output, the pulmonary vascular system, pulmonary capillary wedge pressure, and calculates again the PA pressure. When these two things disagree, the unreliability score is high, and when the unreliability score is high, we're going to say we hypothesize that the model didn't understand, did not capture the underlying physiology, and is wrong. And so that's borne out in the following slide. So for example, if you looked at all of the predictions in the test set and you ranked them by this unreliability score, and you looked at those predictions that fell in the upper 50%, that's the red, and those that fell in the lower 50%, and you looked at the mean square error, also known as the Breyer score for those predictions that have the upper 50% of the unreliability do worse, have higher errors. Let me get my pointer, have higher errors. I could do the same with the upper 25% and the lower 75%, and it's more pronounced. And then the upper 10% and the lower 90%, and it's more pronounced. So when the model does not capture the underlying physiology, as by looking at these different metrics, the prediction is more likely to be wrong. So not only that, we can do the same sort of exercise because the model does look at the pulmonary capillary wedge pressure, which is a value of interest clinically for a variety of reasons. And we see that the AUC, the discriminatory ability for looking at the pulmonary capillary wedge pressure is 0.74 solely from the ECG, which I think is also an interesting thing. And again, if we look at this unreliability score, those that are in the upper 50% of unreliability, the error is higher than those in the lower 50%. In the upper 25%, the error is higher than in the lower 75%. And similarly, those in the upper 10%, the error is higher than in the lower 90%. So, upshot here, we think these physiology-inspired model, in particular, this model I discussed, has a significant discriminatory ability and provides some insight into the underlying etiology of pulmonary hypertension. And by leveraging knowledge of the physiology, can provide additional data that can be tell when the model is incorrect. So I'm just going to go through this last part very quickly because I am running out of time, because it's a generalization of this concept. And this is work really that was done by Anirudh Raghu, a student who I co-supervised with a colleague of mine, John Gutag. It's a new formalism, which I know if Anirudh is looking, he's going to be squirming because we don't use this. This is an old slide, but if you will give me some indulgence. This model in general attempts to incorporate domain knowledge ahead of time and inputs it directly into another model. So what happens before you even design the model, there may be relationships that you understand. Cardiac output tends to be lower in patients with heart failure who have a risk of dying, have a high risk of dying, and higher in those with heart failure who are well compensated and who have a lower risk of dying. So high risk of dying, low cardiac output, low risk of dying, high cardiac output. Those are the sorts of concepts that you can encode as underlying prior distribution. And the model, in addition to making a prediction here, it can present a rationale based on these underlying concepts. So the procedure is called learning to predict and support. And we did one quick application where we had ECG, some patient demographics as input to a model. The domain knowledge encoded was a relationship between hemodynamic parameters and some outcomes. In this case, we looked at death in patients who had an admission for heart failure and went to right heart cath. So we predicted the risk of death 6 months after right heart cath. And the rationale that is made that uses these prior concepts to explain the results. So this learning to predict and support in general has an AUC for differentiating those who die, about 0.74. If you just took a baseline neural network using ECG patient demographics to predict the same thing, it's about 0.75. So they're roughly about the same. The raw numbers are a little bit better for the baseline model, but there's not really no difference between the two. But in addition to that, you get patient-specific supporting evidence. So a patient here is predicted to be at high risk, and you have their cardiac output is estimated to be low, and their systemic vascular resistance is estimated to be high, consistent with a low flow state. We can use these data to actually try to understand the peculiarities around different patients. So if here you have two patients that are both predicted to be at high risk of death, one patient will have a low cardiac output but has a normal cardiac output. So it's not that everybody has the same thing, it's really patient specific. And in line with what I talked about previously in seeing that if the model really captures the underlying physiology, you can trust it more. Similar things are notable here. We can look at these underlying explanations and see what makes sense in light of our understanding of physiology. So I'm gonna just cut. I was gonna talk about some other stuff. I'll
skip all that. I'm going to just mention all the people that did the work. So here, Daphne Schlesinger, who you heard from, did the work with respect to building the models for the pulmonary pulmonary arterial pressures. Nate, who you all know, did a lot of work with pre-training and has just been a wealth of knowledge for people in the group. Anirudh Raghu is the one who's worked on learning to predict and support. Eric Reinertsen did a lot of work early on in getting all of the ECGs together, and these are sort of the other members of the group.